On November 21, 2024, the ISC Mount, a colossal underwater volcano located near the Mariana Trench, the deepest point on Earth, erupted in a mesmerizing yet ominous display of geological power. This extraordinary event unleashed vast plumes of discolored water, potentially releasing floating pumice across the ocean surface and signaling a significant uptick in submarine volcanic activity. In response to this awakening, the Northern Mariana Islands Volcano Observatory swiftly raised the alert level for the seamount to advisory and adjusted the aviation color code to yellow, signaling an increased possibility of hazards to aviation and marine navigation. While the region around the eruption is uninhabited, the broader implications of this event stretch far beyond the immediate area, hinting at powerful processes unfolding beneath the waves and possibly foreshadowing even more dramatic geological changes to come. The seismic awakening occurred at a high seamount, an imposing submarine volcano in the Northern Mariana Islands, situated about 18 kilometers southeast of Farallon de Pajaros. Rising steeply from the oceanic depths, Ahai's summit lies a mere 75 m, about 246 feet, below the ocean surface. As part of the vast Mariana Volcanic Arc, a chain of island and submarine volcanoes stretching across the western Pacific, Ahai is positioned in one of the most tectonically volatile regions on the planet. This segment of the Earth's crust is characterized by a subduction zone where the Pacific plate inexorably descends beneath the Philippine Sea plate. The immense geological pressure and friction generated in this area are responsible for the volcanic activity that gave rise to Ahai and its neighboring volcanoes, continually fueling eruptions and reshaping the ocean floor. The current phase of volcanic activity at Ahai Seamount began subtly in early August 2024, but recent weeks have brought more definitive signs of an ongoing eruption, captured with increasing clarity by satellite imagery. The remote location of Ahai means there are no local seismic monitoring stations in the immediate vicinity, so scientists rely on advanced tools such as hydroacoustic sensors and satellite-based remote sensing to track volcanic behavior. These hydrophones, designed to detect underwater sound waves generated by eruptions, have yet to register strong acoustic signatures from Ahai, a pattern consistent with its previous eruptions. Indeed, historical data reveals that submarine eruptions at Ahai and similar seamounts can generate significant underwater plumes and disturbances without necessarily producing loud or detectable sound waves. As a result, satellite imagery and visible water discoloration have become vital for identifying and understanding such submarine eruptions in real time. The challenges of monitoring underwater volcanoes like Ahai are substantial. Unlike land-based volcanoes, which are often extensively studied through dense seismic networks, submarine volcanoes are typically located in isolated regions and are far less accessible. Scientists therefore depend on detecting anomalies such as surface discoloration, floating debris, changes in sea surface temperature, and gas bubbles that may escape from below. These visual and chemical cues are instrumental in deciphering the intensity and duration of underwater eruptions and in guiding the issuance of alerts for nearby maritime activity. Ahai's current eruption offers a compelling window into the raw power of submarine volcanism and the hidden dynamism of Earth's geophysical systems. This seamount has a storied history of activity, having erupted frequently over the past several decades. One notable eruption was reported in 1979 when the crew of a nearby fishing vessel experienced unusual vibrations and water upwelling containing sulfur, a clear sign of volcanic disturbance beneath the ocean surface. More than 2 decades later, in April 2001, an explosive eruption was detected through seismic signals recorded by a station in the Tuamotu archipelago, located hundreds of kilometers away, underscoring both the intensity of the eruption and the reach of its seismic impact. Between April and May 2014, yet another major eruption was documented using a combination of hydroacoustic sensors, satellite observations, and data collected by NOAA divers. This event dramatically altered the seamount structure, creating a new summit crater and triggering a large landslide on its southeast flank. The scale of these transformations illustrates the seamount's capacity for geological change and highlights the ongoing evolution of underwater landscapes driven by volcanic processes. More recently, Ahai exhibited sustained volcanic activity between October 2022 and May 2023, followed by another eruptive phase from December 2023 through April 2024. These events reaffirm Ahai Seamount's status as a geologically active site and a key location for ongoing volcanic research. Despite its frequent eruptions, Ahai's remoteness has thus far spared nearby human populations from direct harm. However, hazards associated with submarine eruptions, including floating pumice, ash, and other volcanic debris, present serious risks to maritime navigation. Ships operating in the area are strongly advised to remain vigilant, as volcanic material can pose dangers to vessels, clog intake valves, damage hulls, or impair visibility and navigation systems. Understanding the origins of Ahai seamount helps to contextualize its current activity. Like many volcanoes in the Pacific Ring of Fire, Ahai was formed through complex geological processes linked to tectonic plate interactions. At the heart of this formation is the subduction of the Pacific Plate beneath the Philippine Sea Plate, which occurs along the Mariana Trench, the deepest point in the Earth's oceans. As the Pacific Plate descends into the mantle, the intense pressure and heat cause water and other volatiles trapped in the oceanic crust to be released. These substances migrate into the overlying mantle wedge, where they reduce the melting point of surrounding rocks and generate magma. This buoyant magma then rises through the crust, eventually erupting onto the ocean floor to create submarine volcanoes like Ahai. Ahai seamount likely began forming millions of years ago through successive volcanic eruptions that deposited layers of lava, ash, and pyroclastic material onto the seafloor. Over time, these layers accumulated and built up into the towering cone-shaped structure we see today. Although the seamount has reached impressive heights beneath the sea, its summit still lies below the surface and has yet to breach the ocean and form an island. Nevertheless, the sustained volcanic activity suggests that future eruptions could eventually elevate the summit further, possibly above sea level. The growth of Ahai has not been linear or uniform. Explosive eruptions have repeatedly reshaped its summit, forming craters, while gravitational instability and tectonic movements have triggered landslides on its steep flanks. These events are not unusual. Rapid accumulation of volcanic material can lead to structural instability in underwater volcanoes, making landslides a common and often dramatic feature of their geological development. In addition to subduction processes, Ahai's formation is also influenced by seafloor spreading occurring in a nearby back arc basin. This process, which involves the creation of new oceanic crust as tectonic plates pull apart, can supply additional magma to the region's volcanic arc. The interaction between subduction-driven melting and back arc spreading adds complexity to the geological story of Ahai seamount and contributes to its ongoing evolution. Despite its relative isolation, questions have arisen about whether Ahai's recent eruption might trigger volcanic activity elsewhere in the Pacific Ring of Fire. The answer, based on current scientific understanding, is that it is highly unlikely. The Pacific Ring of Fire encompasses a vast expanse of tectonic plate boundaries encircling the Pacific Ocean and includes many different subduction zones, each operating largely independently. Ahai seamount is part of the Mariana volcanic arc, where activity is driven specifically by the subduction of the Pacific Plate beneath the Philippine Sea Plate. Other volcanic systems in the Ring of Fire, such as those in the Andes, Japan, or the Cascadia region, are influenced by distinct subduction processes, separated by thousands of kilometers and lacking direct magmatic connections. However, indirect interactions between volcanoes are possible under very specific conditions. For instance, a powerful eruption or accompanying tectonic disturbance could alter regional stress fields within the Earth's crust. Changes in stress may influence nearby magma chambers, potentially accelerating or delaying eruptive activity in adjacent volcanoes. Yet these effects are typically confined to regional scales and are unlikely to affect systems separated by vast geological distances. Another theoretical possibility involves dynamic triggering, a phenomenon in which seismic waves generated by a major eruption or earthquake travel great distances through the crust and disturb other volcanic systems. In rare cases, these waves have coincided with increased volcanic unrest elsewhere, though such outcomes are rare and unpredictable. For dynamic triggering to occur, the affected volcano must already be on the brink of eruption, with its magma chamber under significant pressure. In such scenarios, the seismic disturbance acts more as a catalyst than a cause, potentially tipping a marginally stable system into eruption. Still, dynamic triggering is not considered a reliable mechanism for linking distant volcanic systems, and it is unlikely that Ahai's eruption will influence other volcanoes around the Pacific Rim. When comparing Ahai seamount to other notable undersea volcanoes, such as Hunga Tonga, Hunga Hapai, the differences in eruption style and impact become particularly striking. Both volcanoes are located in the Pacific and share the common trait of being submarine systems, yet their geological characteristics and eruption magnitudes differ significantly. Hunga Tonga, Hunga Hapai, for instance, erupted catastrophically in January 2022, sending an immense plume of ash and gas into the stratosphere and generating atmospheric shock waves felt across the globe. The eruption had measurable effects on global climate and produced tsunamis that reached as far as the Pacific coast of the Americas. By contrast, Ahai's eruptions, while geologically impressive, have so far been more localized and less explosive. They lack the high-energy ejection of ash into the upper atmosphere that characterizes Plinian-style eruptions like those seen at Hunga Tonga. Instead, Ahai's volcanic output is mostly confined to submarine activity with localized water discoloration, floating pumice, and minor surface disturbances. These characteristics, while still hazardous to marine traffic, do not carry the same far-reaching atmospheric or tsunami risks.